In this video, we'll cover a concept called related rates. The idea of related rates is the following. Often, quantities vary as a function of time, and moreover, such quantities are sometimes related to one another by a specific equation. Then, by differentiating this equation using implicit differentiation, it's possible to obtain a specific relationship between their derivatives as well. For example, suppose that a spherical balloon is being pumped with air in such a way that the rate of change of volume of air is constant, say 0.1 meters cubed per second. In other words, if we let v of t be the volume of the balloon at time t, then we are assuming that v prime of t equals the constant 0.1. This is a reasonable assumption because, for example, the balloon could be filling with air by a machine, which is able to pump in air at a constant rate, which we're assuming to be 0.1 meters cubed per second. Now, another quantity associated with the balloon is its radius, which we'll denote by r. And because the size of the balloon is changing with time, the radius should be changing with time too, so we can write that r is a function of t. The question we'd like to answer then is what the rate of change of the radius will be when the radius is equal to 0.2 meters. In other words, we'd like to know what the quantity r prime of t will be when r of t is known to be 0.2. To find out what r prime of t will be, we'll relate r prime of t to v prime of t. In particular, we know that the volume of a sphere is given by v equals 4/3 pi r cubed. And so, thinking of the variables as functions of t, we have the relationship v of t equals 4/3 pi times the quantity r of t to the third power. To obtain r prime of t, we'll differentiate both sides. On the left, we just obtain v prime of t. And on the right, we get 4/3 pi times 3 r of t squared times r prime of t, where the r prime of t term comes from chain rule. Now, we can simplify the right-hand side a little bit and just write 4 pi r of t squared times r prime of t. At this point, we'd like to solve for r prime of t because that's the quantity that we're interested in. So we isolate it and we find that r prime of t is equal to v prime of t all over 4 pi r of t squared. This way of expressing r prime of t is particularly nice because it expresses r prime of t at any time in terms of both v prime of t and r of t. Thankfully, the problem has given us specific values of v prime and r to work with. In particular, v prime, which is the rate of change of the volume, is assumed to be the constant 0.1, and r of t, which is the size of the radius, is, according to the problem, equal to 0.2. Plugging these into our expression for r prime of t, we find that at this point in time, r prime of t is given by 0.1 divided by 4 pi times 0.2 squared, which is approximately 0.1989. The calculations we've done ensure that the units are correct on this number, and since this is a rate of change for the radius, the units are meters per second. Let's do another example to further illustrate the process. A 12-foot ladder is leaning against a vertical wall when Jack begins pulling the foot of the ladder away from the wall at a rate of 0.2 feet per second. So here is the ladder as the hypotenuse of a right triangle leaning against a wall, and its length is fixed to be 12 feet. Also, here is Jack pulling the foot of the ladder away from the wall at a constant rate of 0.2 feet per second. What we'd like to know then is what the configuration of the ladder is at the instant when the vertical speed of the top of the ladder equals the horizontal speed at the foot of the ladder. Indeed, as Jack pulls the foot of the ladder away from the wall, the top of the ladder is also sliding down the wall at some rate, which may change as the ladder slides down the wall. But the problem asserts that there will be one point in time where the rate of sliding down equals the rate of sliding outward, which is the constant 0.2 feet per second, and we'd like to know what the configuration of the ladder is at that instant in time. For these types of problems, it's helpful to label the relevant quantities which have rates of change. Here, the foot of the ladder is sliding from the wall, so if we label the horizontal distance by the variable x, then we can express the rate of sliding as x prime of t. The problem says that this rate of sliding is a constant 0.2 feet per second. so x prime of t is equal to 0.2 feet per second. Another quantity that's changing is the vertical height of the ladder, which we'll denote by y of t, and it too determines some rate of vertical sliding, which is y prime of t. The problem asks us to find the configuration of the ladder when this vertical speed of sliding, the magnitude of y prime of t, equals the horizontal rate of sliding, x prime of t. In other words, at the instant in question, we know that the magnitude of y prime of t will be 0.2 feet per second. Specifically, because y denotes the upward distance, we know that y prime will always be negative, since the upward distance is decreasing. So, at the point in question then, we know that we'll have y prime of t equals minus 0.2 feet per second. Now, to do as we did with the balloon, we need to relate these rates of change, x prime and y prime, to one another, ideally by an equation which relates x and y. In this problem, since x and y appear as the legs of a right triangle, they're related by the Pythagorean identity, which says that x of t squared plus y of t squared equals 12 squared, since 12 is the length of the hypotenuse of the triangle, which is a constant. From this relation, then, we can obtain a relation on the derivatives by implicit differentiation. On the left, we get 2x times x prime plus 2y times y prime, and on the right, we just get 0, since the derivative of a constant is always 0. Notice that we're using chain rule here on both of the expressions of x of t squared and y of t squared, since they're both functions of the variable t. In total then, we get the equation that is 2x times x prime plus 2y times y prime equals 0. Now, at this point, it's helpful to remember what exactly the problem is asking for. Remember that what we want at the end of the day is the configuration of the ladder, which means that we really want to determine values for x and y to say how far the ladder has slid. Here's one way we could obtain the values of x and y. Recall that at the instant in question, the magnitude of x prime and y prime are equal to one another. Specifically, x prime is equal to 0.2, and y prime is equal to minus 0.2. So we can plug these into the last equation to get 2x times 0.2 plus 2y times minus 0.2 equals 0. Solving for y in terms of x, we find that y equals x. Now, to find the exact values of x and y at this point in time, we'll just use that they're legs of a right triangle, satisfying the relationship x squared plus y squared equals 12 squared. Since y equals x, we can write x squared plus x squared equals 12 squared, and solving for the positive version of x shows that x equals 6 times the square root of 2. Since y is equal to x, we have that y is equal to 6 square root of 2 as well. In total then, the configuration of the ladder at the instant in question is the one where the foot and the top of the ladder are both 6 square root of 2 feet away from the corner of the wall.